about our efforts to enhance our Kia GPS receiver. Okay, so for those of you who don't know, we've been doing GPS for a long time at AXA, and also before AXA at School of Spain. So started doing this around 2003, 2004, and during that time the project was basically for research, a bit of a hobby, not much happened with it. And that is until we got an ASRP grant from the government, which was a really big grant, and DSTG got interested. So anyway, DSTG came along and go, oh yeah, you've got this project to do some GPS, and how would you like to fly a GPS on a CubeSat? So we go, oh yeah, that sounds pretty exciting, but all we've got is this. And we showed them the Nanu version 2 that we had, and we said, oh, it's a bit big, and yeah, you should just go out and buy an Novotel. Well, DSTG weren't too interested in that. They were pretty keen that we go away and do something. So they convinced us, yes, you should build a new GPS receiver. And we ended up producing this, which is the Nanu 3.2. So that took a lot longer than we expected it to take. Anyway, we did the work, and I got a trip to AFRL in Albuquerque. We talked to them. They eventually integrated it into a CubeSat, which was the AFRL Shark CubeSat, and it navigated. In fact, it navigated about 4 years ago. I remember sitting inside the baby physio while my daughter was in there and getting an email saying, here's a log. Oh yeah, navigated, fantastic. Very, very good. And that actually became the very first Australian and New Zealand fully designed and built GPS receiver in navigated space. And even more gratifying, the other GPS receiver on board that mission failed. So it was the only mission on that thing that gave us our GPS positions. Anyway, so after that, the money ran out, so what was going to happen next? So myself and Kevin, partners in New Zealand, decided we'd take that design and kind of upgrade it a bit. So we've got a new processor there, we did a new RF board, converted all the software over, and that became Kia. And we sold a few of those. We flew on Buccaneer Risk Mitigation Mission, became the second fully Australian designed GPS receiver in navigated space. And we've sold a few of those since then. And you can still buy them. Kevin sells them, he's built a few more of them. And that's the end of that. Okay, so what's the problem with that? Well, unfortunately, since then we've started to do other things. And a single frequency GPS receiver with a rather low power processor isn't doing what we needed to do. So, for example, one of our interests at the moment is GPS reflectometry. And to do that, you need 2 radios. That's got 1 radio, no good. There's other things called GPS radio occultation. You need dual frequency for that. There is a dual frequency. The processor is quite low power. It's not a very super powerful processor. It's 100 megahertz Cortex M3. And if you want to process Galileo and Beidou and all these other signals as well as GPS, then you run out of steam pretty quickly. And its update rate's pretty slow, so 1 hertz update rate. So not all that great for things that are moving really fast, like rockets. So, and the FPGA fabric's quite small, so it's got 60,000 logic elements, that particular FPGA. So when the Australian Space Agency had their submissions for grants, we put in a case to upgrade that, and our case must have been sufficiently strong because they gave us the money, so that was good. Okay, so what did we propose? Well, what we wanted to do was be able to process some other constellations. So that Galileo is one that the Europeans have been working on. It's almost complete, so there's not as many Galileo satellites as there are GPS satellites, but it's a nice constellation that we put together. So we wanted to add Galileo to the software. GPSL5 is something that we've been interested for a long time. In fact, the Garada project that we did quite some time ago tried to do that, and we had all sorts of problems, so that wasn't a great success. So we put that in. The remote sensing application requires you to look at reflected signals. You need special correlators to do that. So we want to be able to do that. We need a much bigger FPGA, needs to fit inside a CubeSat, want to be able to do dual frequency with, you know, 2 antennas at least, so each antenna can do dual frequency. And we also have this concept of trying to do things with spinning rockets, so having like multiple antennas all around the circumference of the rocket, and if the rocket's spinning, then trying to see if we can navigate despite the fact that the signal's getting chopped up as you go round and round and round. So the last thing was data streaming. So we found for quite a lot of our experiments, you want to fly somewhere, collect some data, and then give the data to a student or whatever, and try and do interesting things with it. Okay, so those were the requirements. What we ended up with was this. So this is our design. We had to sort of, this isn't quite what we proposed. It is what we ended up with after about 4 months worth of trying to do something else and suddenly realizing, oh, actually we can do it in a better way. So the current design is using a new part called the PolarFi SoC. So that part is sampling at the moment, so it's not in full production, but you can buy engineering samples, EVK boards or whatnot. We've got 4 Next 2771 RF front ends, and those are quite a common chip now. It's sort of newish, but that's taken over from another part. We've got a special USB 3 chip on there, which will do USB 3, and let us get data out of it very quickly. And the FPGA up here is 250,000 logic elements, so maybe 4 times bigger than the other one, so quite a nice big piece of logic. That's the design, and the processors are RISC-V, so that's new sort of processor type stuff. All right, so you can imagine if you try to build that sort of hardware, it's pretty risky. So what we've ended up doing is we've ended up doing all the software development on this cobbled together setup that you can see there. That's the PolarFi SoC FPGA board. This is the little board that lets you test out the RF front end, and that's the board that lets you test out the USB 3. So that's what it looks like when it's in the bench. The board's made up there, I soldered them up. One of my other engineers soldered that up. We've got that working. It works surprisingly well, and we've been able to use that to get all that FPGA stuff working along the software. In the meantime, we had a fellow in New Zealand, and since this was an international space initiative, we had to collaborate with someone overseas. That was the guy in New Zealand. He designed this, so that's the board that's ended up being designed. It took a long time to get it done. We received these boards at the start of this year. And unfortunately, neither of them worked. So the power supplies of this were producing the wrong power, and then he tried to fix it and he shorted out things. The other board has a short on it. They're basically 2 paperweights. So that was quite disappointing. So we'll need to build some more there. Now, this is where the effects of the pandemic become evident, in that you actually can't buy parts. So these radios you can't buy. In fact, Craig was telling me how he had to bid for lots and lots of those chips because he was one of the last buyer of them. So these are hard to get. This chip went into production. I think they did a production run earlier this year. We can get special samples if you say you're building a prototype. We're getting sometimes hopefully in dealing with the guys already. And these are the USB 3 chips. I was lucky enough to find someone now, so it's 6. So, right, we'll buy them. Thank you very much. So we'll have another crack at building that. But in the meantime, you might think that's terrible, you know, it's all a big failure. And actually, you'd be completely wrong there. Because actually, a lot of this program, or this project, is more about FPGA design and firmware. So, you know, whenever you're doing this sort of work, your firmware and your FPGA is the stuff that has the longest life. The actual hardware designs, they change all the time. So, you know, our software has been, you know, there's 15 years of work in that. And when a new hardware comes along, we support it over the new one, keep going. Whereas your hardware is themselves, you know, new parts come out and then we spin the board to port it and carry on. So what have we done? Well, the correlator's been completely redone. So now they they always did do GPSCA code. They do Galileo, which is a memory code system, which is different. GPS L5 is really high frequency bandwidth, so that's all new, that works. We've got, oops, that wasn't what I wanted. Turn it off. Okay, there. Oops. There we go, all right. The correlators themselves do little delay Doppler maps, which is needed for the remote sensing thing. So we've got little FFTs and it's little, you can pick how many taps you've got per correlator, and all of those are configurable. So we can probably increase that A pretty easily. This number can be made to be whatever. You've got enough logic, make it as big as you like. Quite a lot of new firmware. So the firmware is all written in C. Some new firmware needed to track the new signals, which have slightly different structures, and also the navigation messages that the satellite transmit are quite significantly different compared to the old ones. So the new signals have like forward error correction and determined decoders, big CRCs, messages are all different. So a whole bunch of new stuff has gone in there. We can now navigate with Galileo U1, so that all of that stuff works. We can extract the CNAV messages from GPS L5, so that works. And we can track the GPS L5 signals, that works. We're actually producing pseudo ranges for Galileo or GPS L5. Haven't quite navigated with it yet, but that's pretty close. I think we'll be navigating within another couple of weeks. So lots of work has gone on there. It's all moving along quite well. These are the people who've worked on it in some form or other. The top fellow who's got Canberra since then, Ryan, he did all the forward error correction and the data decoding stuff. Kurt worked on the USB 3 stuff. He's now gone and joined the RAAF. Kevin in New Zealand. We've had a student who did as his project the thing to do with the spinning antennas, and he did quite a good job on that. That's hopefully we'll get to present that at maybe the IGSS conference or the SRC conference. And Andrew and Michael will be dealing with the Space Agency, doing all the administrative stuff.